Hello again. All right, so now we are going to talk about how to actually find these eigenvalues, eigenvectors, and eigenspaces. Okay, so I'm going to work out an example in detail, explaining as I go along. You'll be able to do this type of example a lot more quickly. This first time through, I'm using it to explain. All right. So suppose you're given a matrix and you want to know what are its eigenvalues, what are its eigenvectors, what are its eigenspaces. Well, that means you're answering this question. For what a vector x and what eigenvalue lambda will it be true that ax is the same thing as just lambda x? And again, you don't want just x equal to 0. That would always make that true. 0 is equal to 0, right? But the non-trivial solutions, x not equal to 0. Can't be an eigenvector without being non-zero. So you're trying to solve this equation. If you subtract the lambda x over, you've got this. If you insert an identity matrix in here, which you can, it doesn't change anything, then you are able to see these on the level of matrices, and those are column vectors, so you can factor those out to the right, and you're left with this. Let's let b equal to a minus lambda I. Ask yourself the old question. Good review for the beginning of the semester, right? When does bx equal to 0? Other than x equal to 0, right? What are the non-trivial solutions? Well, we certainly don't want b inverse to exist, because then b inverse multiplied on both sides on the left there would just give us b inverse bx equal to b inverse 0. b inverse 0 is just the 0 vector. B inverse times B is the identity matrix, and that just gets us x equal to 0 again. So no having x invertible. Well, that means, remember determinants we just were talking about? We need the determinant to be equal to 0, because the determinant non-zero means the matrix is invertible. We don't want that. So we want the determinant to be equal to 0. So replacing B with a minus lambda I, we need the determinant of a minus lambda I to equal 0. This is the defining equation that helps you find lambda, so it's called the characteristic equation of A. The roots of that equation are your eigenvalues. So we need the determinant of a minus lambda I to be equal to 0. Remember another way of writing the determinant of a matrix, that's all one big matrix B, right, is to use straight lines, and that helps in this situation. So I'm looking for the determinant of a minus lambda I. What does that look like? Here's A, here's minus lambda I. That means this matrix, we're taking the determinant of this matrix minus multiplying the constant through by every term in there, we get this lambda I. And that shortens, if you add those two, or subtract those two matrices, you're looking for the determinant of that. Well, that's 5 minus lambda squared minus the cross diagonal, which is 9. That gives you a quadratic polynomial in lambda, which, if you're careful about how you multiply things out, if you thought that was 25 minus lambda squared, that means you're forgetting your basic algebra. Go back and remember about cross terms. Yes, they do affect 2318 students, so review. So we end up getting this equation, quadratic equation, which can factor and give us these two roots. From algebra, we know that if it's a second degree polynomial, it has at most 2 roots. If we have found them, then we have found all its roots. And therefore, we have found all the eigenvalues of this matrix A. So now we just go back and solve using lambda equal to 8 or lambda equal to 2, that original system, right over here. But now we're going to be solving for the x. Now we're solving for the eigenvector. So for each lambda, one at a time, you stick in lambda equal to 8 or lambda equal to 2 in there and solve for the corresponding x. Okay. You should stop the video, try that. Okay. Let's say you come back. We hope you come back. And let me get rid of that glare. Okay, so let's see. Maybe I'll move it over here. And that doesn't get rid of the glare. So I'm back up here. Alrighty, so that you can see this for sure. What do we got? All right. So when lambda 1 is equal to 8, ax equal to lambda x, or ax minus lambda ix equal to 0, or solve this augmented system. If you replace the lambda with an 8, you get this. So 5 minus 8 on the diagonal. The 3's aren't damaged, aren't changed at all. The off diagonal is not. Again, you just saw why that was. So you simplify that and you get negative 3, 3, 0, 3, negative 3, 0. Well, by adding row 1 to row 2, you would get all zeros in the bottom row. Multiplying the top row by negative 1/3, you could get something like this. You don't have to get this, but this is nice. What does it give us? That this matrix times x is equal to 0. Well, go back and remind yourself what x looks like. Right? X is a vector, column vector that you're multiplying by this matrix, so it just has two components, x and y. This is that old business about, do you know how to, once you reduce, putting Gauss, reduced row echelon form or something equivalent, do you know how to go back and interpret the solution? Very key, once again. So we have, if you multiply it by components, you get that x minus y has got to be equal to 0, or that x has got to be equal to y. These are the two components of that vector, x. Alrighty, so you could take it this way. You could say, well, let's let y equal to s, and since x is equal to y, that's also going to be s. So an eigenvector has to look like a vector that has the two components the same. Call them both s. Notice you could factor that s out and have the vector 1, 1 being multiplied by any s, where, well, as long as s is not equal to 0, or some real number, then you're good. A sleek way of putting all that together is to write it this way, that this is now the eigenspace. Okay, the eigenspace for lambda 1 equal to 8 is the set of all two-dimensional vectors in R2, such that x is equal to some constant multiplier by 1, 1, for example. You could have put 2, 2 there. You could have put pi, pi there, right? Where s is anything in R star, which means any real number not equal to 0. Okay, so that's the eigenspace done. If you need an eigenvector, you could use 1, 1. You could use 2, 2. You could use pi, pi. You could use anything vector that has the two components the same, if you needed just a single eigenvector. But here is all infinitely many of them at once, so we call that the eigenspace. When lambda is equal to 2, again, we are solving a minus lambda I, but with lambda equal to 2. Now we have 5 minus 2, 5 minus 2. Well, that's just going to be 3's and 3's. So now we have this, which is row equivalent to that. You can figure that out, which row operations would do that. And again, remembering that x is a two-component vector with real numbers x and y. That matrix multiplied by this would give you x plus y is equal to 0, or y is equal to the opposite of x. So an eigenvector for lambda equal to 2 looks like some multiple of something like this, where these two components are opposite in sign, and t is some scalar out here as long as it's non-zero, a real number. How do you put all that together in one easy line? You say E sub lambda 2 is equal to the set of all vectors in R2 such that they are equal to t times that constant vector 1, negative 1. Again, you could have chosen anything there, as long as t is non-zero, real number. So those are two eigenspaces. And again, if you need to just grab some eigenvectors, for lambda equal to 8, you could grab 1, 1. For lambda equal to 2, you could grab 1 minus 1. You're going to be doing that kind of thing later, actually, needing a couple of eigenvectors from each eigenvalue next week. All right, so what does that tell us about what's going on with this dynamical system? Oh, that's the next door neighbor playing with this kid. Sorry about that. Okay, so here we have when x is equal to y, that's when lambda is equal to 8. Look what's going on. Okay, so if a point on the plane is somewhere along the line y equal to x, then when you apply t sub a to that vector, that's some constant multiple of 1, 1, you're going to get, well, that's a linear operator, so you get c times t sub a of 1, 1, which is the same thing as a times 1, 1. And that's the same thing, since 1, 1 is an eigenvector for lambda 1 equal to 8. That looks like c times 8 times 1, 1. And so what you end up getting is that this is equal to 8 times whatever that original vector was. All right, so any point along here, what's going to happen to it? It's going to, its length is going to be increased. It's going to go on in the same manifold, but length is going to be increased by 8. So any point along there is just going to be shot out that way. Similarly, if you start with a -1, -1, multiply it by 8, it's going to be shot out that way. All right, so anything on that line is moving away from the origin. Looking at when lambda 2 is equal to 2, we get this line. This is e sub lambda equal to 2. Okay, that's the line where y is equal to the opposite of x. Again, anything that's on that line is going to be, any vector is going to have its length multiplied by 2 and headed out further along that direction. Or if it has, if it's over here, then it's going to be something like, let's say 1 minus 1. If you multiply that by 2, you get 2 minus 2, again, further out along that line. So we understand completely what's happening along those two lines, but also want you to get used to this idea that we actually can tell what's happening with any vector x. Any vector x could be written as a linear combination of these two. Again, here I'm taking, or I could take x1, an eigenvector for lambda equal to 8. I could call that 1, 1. And for x2, I could use for that any vector of this form where they're same magnitude but different in sign, so I could call this one x2, right? Notice that they are linearly independent. So I could write any vector in the plane as a linear combination of those two. If I then apply the transformation t sub a on there, well, that multiplies everything on the left by a, and that just distributes through there. The constants come out. And notice that the ax here turns into an 8x1, and the a on x2 becomes a 2x2. So if you applied it again and again and again, this transformation, you're going to get this, that x1, its magnitude is going to be multiplied by a factor of 8 to the n, which is much greater than this. In fact, it's 4 to the n greater than this. So what's going to end up happening is that this, I should color that in blue because that's this manifold. This part is going to dominate if you keep applying this map again and again and again. So this, if you run this dynamical system a lot of times, keep iterating this map, you're going to end up getting things moving parallel to this line, anywhere parallel to this line, but away from the origin, okay? And so what we end up saying here is that 0 in this case is said to be a repeller, so the opposite of an attractor. So it's repelling any points that start near it, get shot away. And either of these linearly independent directions.